So I'll just dive right in. So today I'm going to tell you about two projects that I've worked on roughly the last year. One project I'm going to tell you about is how we build this purple thing, which is an overapproximation of the robot's reachable set. And then in the second part of the talk, I'm going to describe how we combine these reachable sets with Gaussian splats so that we can do planning and radiance view. All right, so before I get started, I wanted to motivate this talk by something that I find really interesting. And that is that AI recently won the Nobel Prize in Chemistry this year. If there are any hot takes, we can talk about that later. But this is actually a really important problem because getting the structure of a protein is one of the notoriously difficult problems in the life sciences. And the reason it's difficult is because it's really challenging to find the right experimental conditions, including temperature, pH, ionic solution, to really coax a protein into forming a crystal lattice under which you can get a structure. And so I think to the layperson, it seemed like DeepMind and Co. sort of solved this really challenging problem overnight. But in fact, the story actually started much earlier, about 200 years earlier, with the discovery of these molecules known as albumins. So this is sort of the first discovery of protein. If you fast forward 200 years, about 200 years, we get the first crystal structure, the first crystal structure of a protein called myoglobin. So some of you may know that this is the protein that transports oxygen in muscles. Fast forward another 20 years, we get the establishment of the protein data bank, which houses not only protein structures, but also protein interactions and nucleic acid structures. And you can see here that the number of structures is, this looks like it's growing sort of exponentially every year. And then in 2011, we get the establishment of the modern deep learning era with the publication of the AlexNet paper. 2017, we get the attention mechanism and the transformers architecture. And then in 2021, DeepMind publishes the AlphaFold paper. And then in 2004, the rest is history, they won the Nobel Prize. So what I want you to take away from this is that AlphaFold was trained on nearly 50 years of clean, well-curated crystal structure data. And so me being a former biologist, the question that I ask is, what's next? So the way I think about what's next is to think about biology in sort of two different paradigms. So here I'm going to use an engine and engine parts. Sorry. So AlphaFold is the foundation model, if you will, trained by DeepMind that predicts protein structures. So basically what they did was they took this database, this protein databank, they trained on about 200,000 protein structures, and then they were able to predict structures for virtually every known protein. Not necessarily. I think if you were a super duper AI nerd, you would know. So I'm not assuming that you are, but maybe some of us in this room. Okay, so the way that I think about, there's two ways that I think about biology, and I'll use this car engine analogy where engine is cell, and then the proteins, the parts of the proteins. And so historically what's been done is that we've looked at these parts in great detail using the tools from biochemistry and biology structural model. And we try to infer how these engines or cells work. This is really difficult. And I think that there's another paradigm which might be more informative, and that's studying the engine directly and trying to understand how these parts or proteins work together to do things inside of live cells. And so this is what I have a lot of experience doing. So my former PhD, I was studying how cells generate forces and developing embryos. So here's an example here. You can see these accumulations that are forming, and that's the surface of the cell contracting So this is a really important process. It happens all over the place. It happens when the cell crawls, or when the cell divides, or when the tissue bends during development. And what I'm showing are a bunch of proteins. These are the kinds of things that AlphaFold can predict the structures of that are involved in this process. So what I did was I made quantitative measurements of these things inside of these cells, and I was able to back out a mathematical model of how this works. And so what I learned in the process was really that the whole is greater than the sum of its parts. And then, with the recent Nobel Prize being awarded to AlphaFold, I started to wonder, why hasn't cell biology had its AlphaFold moment? And I think the answer is because doing biology is actually very difficult. So it can be difficult to design experiments to study really complex systems, like this embryo that's zippering its neural tube. It's difficult to handle solutions. So putting protein or RNA in solution is very difficult because they tend to denature. It's not obvious how to scale up a lot of experiments. So the person who collected this is an exceptional experimentalist, and I'm pretty sure he's the only person in the world who can do this. So how do you scale the collection of this kind of data when there's only one world expert? On top of that, it can be difficult to reproduce experiments, both within a research lab and across research groups. And then that isn't bad enough. Your experiments might kill you. And so the takeaway is that cell biology lacks, and other fields in biology, lack large amounts of high quality data to train these large AI models. And so I think the solution to that is to build robot scientists. So this isn't exactly a new idea, because the pharmaceutical industry has put robots in research labs for a very long time, but they tended to be more of the automation style robots, which I'm showing on the left. So at the top, there's a liquid handling robot that's just moving liquids around, and then more or less pick and place robot that just integrates equipment by just placing plates and things in different machines. But I think that these kinds of robots need to be enhanced with more general autonomous robot scientists. And so what these robots are doing are things that are more similar to what a dexterous, expert human scientist would do in a research lab. Sure.
Source of energy. I mean, movement doesn't happen out of the sky. It has to have an energy.
So you're asking, so you're asking for an example like this.
Yeah.
So I can answer the question, where does energy come from? Absolutely. So the way this works is that you have molecules like this, which is myosin. So you might be familiar with the myosin that's in your muscles. It turns out that that molecule is also inside nearly every other cell. And it uses the hydrolysis of ATP, which is an energy source, to squeeze things and shift them around. So this is a cell. So it has its own metabolic processes that are producing energy. It is fascinating. And that's why I spent, X amount of years studying it. We don't have to talk about how long it was. Okay. So the question I've been asking myself lately are, what are the requirements for a robot scientist? And I think some of the requirements are pretty obvious. First, the robot needs to perceive its environment. Research labs tend to be semi-structured. They're dynamic with people and instruments moving around, and they're also full of transparent objects that can be difficult to detect. Robots also need to be able to learn behaviors, especially as an experimental workflow begins to change, right? We don't just continue to do the same experiments over and over. And this can be difficult because if you're teaching a robot directly on real hardware, it can be expensive to collect real world data. And if you do all of this in SIM, crossing the SIM to real gap is still non-trivial. And then lastly, the robot has to actually go out and do real work in the real world. So that means that everything the robot does should be in real time. The robot should be able to reason over contact as it's grasping and manipulating different objects. And then lastly, and maybe more importantly, the robot should be safe. And so the question I've been asking myself for the past year is, what are the correct representations for addressing these challenges for enabling robot autonomy? And so here's a preview of some of the results that I'm going to talk to you about today. Like I mentioned at the beginning, I'll talk to you about two different projects. The first project is how we build a safety set around the robot. And then in the second project, I'll describe how we integrate that safety set with Radiance fields so that we can plan directly from visual input. So I just sort of mentioned this, so I'll just go past. All right, so here's the safe motion planning problem that I'm trying to solve. So I would like to move the arm from some initial configuration shown in blue, the desired configuration shown in green, and I'd like to be able to move the arm safely. And here, my definition of safety means that the robot should satisfy its actuation limits. So this means that the robot should satisfy its position, velocity, and torque limits. So what this ensures is that any trajectory that the robot will follow is actually realizable in the physical system. And then lastly, the robot should avoid collisions with obstacles in the environment. And the way that I typically approach this is by applying a hierarchical planning framework, where at the highest level, there's a high-level path planner that generates discrete waypoints between the start and the goal. At the middle layer, there's a trajectory planner that specifies the positions, the velocities, and the accelerations as the robot's moving between waypoints. And then at the lowest level, there's a tracking controller that ensures that the robot can actually track the trajectories that are generated by the trajectory planner. And so what I'm going to talk about today, all of the safety constraints that I'll talk about today are enforced in the trajectory planner. And so I'll approach the trajectory planning problem using a receding horizon framework. And so here I'll assume that the robot has access to a high-level planner that can generate discrete waypoints between the start and the goal, but I won't assume that these waypoints are collision-free. So we might actually have a high-level planner that gives us unsafe waypoints, and the trajectory planner has to deal with that. And so the question that I want to answer in this section is, how should the robot enforce safety while it's planning trajectories between consecutive waypoints? Okay, so there are a number of ways to think about robot safety, but I usually think of two broad categories. The first category involves discrete time representations. So here, safety is only enforced at particular time points. So, but unfortunately, this introduces a trade-off. So the robot becomes more safe the more finely time is discretized. So the more often the robot checks for safety, but this can make it difficult to generate motion plans in real time. The other category includes continuous time safety representations. Right, so broadly speaking, the way these kinds of methods work is you overapproximate all possible states of the robot over some finite time horizon. And you enforce safety using some large overapproximate set. But these methods are also difficult. They're difficult to compute, especially when you want these representations to be, if you don't want them to be overly conservative. And you can also imagine that these kinds of representations can be difficult to compute when you have a really high degree of freedom system, right? So imagine generating representation for an arm versus a full human. And so the key idea behind what I'm going to tell you about in the first part of my talk is that in order to build these reachable sets, we're going to combine interval arithmetic with classical robotics algorithms like forward kinematics or inverse dynamics. And then we're going to combine those to compute the reachable set. Okay. So just to make sure we're all on the same page, I'll give more mathematical definition of what a reachable set is. So if you consider a dynamic system, x dot, some dynamics f, and you consider an initial set, your system can start, so xi, then the forward reachable set is a set of all states that can be reached from this initial set under the dynamics over some finite time horizon. Okay. And we have a few assumptions before we get into building a reachable set for this arm. First is that, so firstly, I'm only generating reachable sets for serial 7-degree freedom manipulators. I'll assume that each joint is revolute. This isn't a very restrictive assumption. We can relax this assumption, but just in this talk, every joint is revolute. I'll assume that the volume occupied by each joint can be overapproximated by a sphere. So if my arm is a robot, I can put a sphere and that'll encompass the volume that's occupied by my elbow. And then lastly, each link is overapproximated by a tapered capsule formed by 2 consecutive spheres. And actually one more thing. For now, we're going to assume that all of the obstacles are boxes. And just to be clear, I'll assume that I know where all of the obstacles are, how big they are, and how many there are in every in each environment.
Paper capsule is a spheres connected by cube.
Yeah, so it's
The tapered caps, I was asking about the tapered caps. Tapered.
so the question is, what is a tapered capsule? It is, so if you have 2 spheres, they might not be the same size. It's the convex hull of these 2 spheres.
The boxes assume to be axis.
Yeah, so here I'm assuming that they don't need to be axis aligned, but in all the examples I'm showing you, they are axis aligned.
Okay, but it's not fundamental, but they
No. Are there any other questions? We don't have a restriction on overlap. Okay. So here's a very brief overview how I'm going to construct a reachable set. I'll start by over-approximating the trajectories that the robot can follow. And then I'll feed these trajectories to a set-based formulation of the forward kinematics algorithm. And then from there, I'll walk through how we build the spherical over-approximation of the robot's reachable set.
First question.
Absolutely.
I'm confused by like why you need a reachable set that's not a specific point. Like, if you know where the robot is now, like isn't there, one place it will be at each point in the future?
Let me make sure I understand your question.
Like the set xi in the definition of the reachable set, like,
Yeah,
I guess that's coming from the over approximation of the trajectories, is that right?
I think I'm not quite sure what your question is.
Like my question is if I know the current state now, exactly, which maybe isn't true. Like then the reachable set ought to be like have no volume. That's what I would expect.
I understand your question. The challenge is accounting for time. So I might know where the robot is at time ti and ti plus 1, but what happens in between?
But don't you know the dynamics of the robot, or you're assuming you don't know the dynamics?
I think even if you do know the dynamics of the robot. So how would you compute it exactly? I think is my question.
Okay, wait, maybe I'm realizing my mistake here is that like the volume is coming from the volume of the robot too.
Yeah.
I see, okay.
Yeah. So CAD software has done this historically, like computing swept volumes of objects. And at best, they have really good approximations.
Yeah.
And sometimes it may take a long time to compute. And so what I'm describing is something that can can be computed fast enough to do real-time playing.
Okay, thank you.
Okay, so in order to build these reachable sets, so reachable sets for both the joints and the robot, we will need this particular set type called a polynomial zonotope. So it's just a set, but it's characterized by a few different vectors, a vector called the center and vectors called the generators. And each of these generators are multiplied by indeterminate coefficients. Okay, so these are just numbers to live in the interval -1 to 1. Okay. But we can do a lot of operations on polynomial zonotopes. So we can slice them. This is just a fancy way of saying we can plug in actual values for some of these indeterminates. We can overapproximate polynomial zonotopes by intervals. Meaning we can put a bounding box around them. And if we have two polynomial zonotopes, we can add them together. So computing their Michaux sum. And if we have a matrix and a polynomial zonotope, we can multiply, we can compute their product. Okay. And then lastly, we can also do set value function evaluation. And so what this means is that if we have a function f that's analytic, so a function like sine or cosine that has an infinite Taylor expansion, we can actually evaluate what that function will look like if we pass in a polynomial. And lastly, we can overapproximate this set value function evaluation with another polynomial set. And so the thing that I want you to take away from this is that we can do a lot of operations on these polynomial zonotopes, and they're more or less intuitive. And that these operations are either exact or overapproximated. And so we're going to need this property to ensure that we overapproximate the reachable set of the robot. Okay. All right. So next I'll tell you about the parameterized trajectories that we use. So these are the trajectories that we optimize over when generating motions between the start and the goal configuration of the robot. So each desired trajectory is parameterized by this vector k. All of the trajectories I'll tell you about are finite. So they all start at 0 and they all have some finite time horizon. And then because we care about safety, all of our trajectories have breaking points. So the final velocity and the final acceleration, they're all 0. Okay. And then one thing to note is that there are many different trajectories that we can use. We can parameterize them in many different ways. You can parameterize final position or velocity or acceleration. Here's an example where we parameterize this trajectory using a constant acceleration. But like I said, there's many ways to do this. You can use more complicated polynomials like Bernstein polynomials or Bezier curves. Okay, so now that we've defined our desired parameterized trajectories, I'll show how we overapproximate. So we start by overapproximating by representing trajectory parameters as polynomial zonotopes. We then represent time intervals also as polynomial zonotopes. We plug both of those sets, Ti and K, into the polynomial form of our desired trajectory. And then if we happen to have any tracking error in our system, we can also represent that as a polynomial zonotope. And then we can use a Michaux sum to add these together to get an overapproximation of our final limit of our trajectory. And one thing I want to point out is when we actually choose a trajectory parameter K, that's choosing an individual trajectory that a joint will follow. Question?
Yeah, it's considering discretized time, or am I reading too much into the box?
So we have chopped up time into intervals. Right, so we're not considering just discrete time points. We've chopped a continuous interval into subintervals. And then those subintervals are sets for polynomial zonotopes that we just pass into the function for our desired trajectory.
And I guess is the size of that interval a parameter that controls how maybe conservative you are, or and does it change how fast, I guess, the computation is?
Yeah, absolutely. So, yeah, the more time intervals you have, the less conservative it can be. But in practice, lots and lots of time intervals slows down computation. So for us, we usually use about 100 time intervals. There was some work in the lab where people were trying to build these kind of reachable sets for humanoids, and they had to use 1,000 to make them not overly conservative.
Going to like my previous question, it seems like part of the volume is coming here from like K being in that parameter set. Can you clarify like why it's helpful to consider like a set of parameters instead of just saying, I know the trajectory I'm trying to track?
Yeah, that's a great question. In principle, you can do that. So essentially what I'm building up to is over approximating a bunch of different trajectories that the robot can follow. And then solving an optimization problem to select out a trajectory that satisfies all of my conditions, right? But to your point, everything I'm doing, I can treat as like a verification step. So if I knew exactly the path that I want the robot to follow, I could build something that was less over approximated. That's a great question. And then just note, we can also build a similar joint velocity reachable set. So we can also over approximate the velocity of each joint in a similar way. And so the main thing to take away is that for each trajectory that we can choose, our actual desired trajectory lives within this over approximation. And so this guarantees that when the robot follows this trajectory, it will remain safe. Okay. So now that we have our over approximated trajectories, we can then use them to build a spherical coordinates, which is just an over approximation of the robot's reachable set, and it's composed entirely of spheres. So I'll try to walk through this slowly, but please, if you have questions, just interrupt me. Okay. So for each time step, we select out interval representing the position of representing the joint position. We pass this to forward kinematics algorithm. So it's a PZ forward kinematics algorithm, meaning that it does the same kinds of operations that the forward kinematics algorithm does, but now it's using interval arithmetic or polynomial zone-to operations. The output of that is an over approximation of the position of each joint frame. Okay. And an over approximation of the orientation of each joint frame. And so that's what I'm showing here. So these polynomials over approximate the position of these two joints. The next thing I do is over approximate these joint position PZs with spheres. So now spheres are over approximating the position of each of the joint frames. And if you recall earlier, the assumption, the volume occupied by each joint is a sphere. So I've added these joint position spheres to the joint volume spheres to get what I'm calling the spherical joint occupancy. So this is an over approximation of the positions of the volume occupied by a joint over a particular time interval. Okay. And then from there, we add in another collection of spheres, and now we've over approximated the link volume. So I won't really go into the math, but we've overlapped these spheres in a way to ensure that it's actually over approximative of the robot's behavior.
There's discretely many,
Yeah,
but you've done it in a clever way that like you don't lose anything.
exactly. Yep. Any questions? Okay. All right, so now that we have an over approximation of the robot's reachable set, we can then combine it with a time distance function to compute our obstacle avoidance constraints. And so the key idea here is that if we can enumerate all of the vertices of all of the obstacles, then we can represent the collection of obstacles as an exact sign distance function. And so what this boils down to is if we can enumerate the vertices, then we can compute the distance between any point in 3D space and the faces, the edges, and the corners of each of these obstacles. And we collectively can represent that as a sign distance function. Okay. So we have this nice theorem that says sign distance function between, if the sign distance between, each center, so of the spheres that we've computed, minus its radius is greater than 0, then we're guaranteed to be collision free. Okay, so essentially I've walked through how we build an overapproximation for position, velocity, and how we ensure obstacle avoidance. One thing that's missing here is the input constraints of the robot. So I didn't really talk about that, but we do know how to overapproximate the inputs of the robot to guarantee that the robot isn't generating forces that are too large to be realized in the real system. Okay, so here's a comparison between our method, which I'm calling sparrows, and a few other state-of-the-art methods. So we're comparing to QRobo, which is a method that was from a paper published by NVIDIA last year, Traject, MPOT, and one of the other papers that I've written called Armor. So what you'll see is that QRobo, Traject, and MPOT all experience collisions before the robot can reach the goal. And you'll see that Armor remains safe, but it gets stuck before it reaches the goal. And sparrows will actually reach the goal.
Follow me before I formulate my question. Is the reason that the first three crash because there was some uncertainty in the obstacles, or?
Yeah, that's a great question. So we're assuming that each of these robots has perfect knowledge of the environment. So they know where all of the obstacles are.
Okay, then why do they crash? Like what, is it that you can discretize finely enough for like an equal apples to apples amount of compute, or like how do you?
So we did do a hyperparameter search for each of these methods, and there's also another method that I'm not showing called Chomp. And this was essentially the best. This was the best we can do. I think the collisions are coming from. So technically, this paper doesn't have a hard collision constraint, right? So it has a penalty in its cost function. So that won't ensure that the robot is collision free. This paper, John Schulman's paper, is enforcing a hard collision constraint. It's even using swept volumes, but it's not really computing the swept volume the correct way. This paper is enforcing collision avoidance only at discrete time.
For Traject, what do you mean by it's not computing set volume? Correct way.
So,
Sorry, just get security.
no, it's fine. So the output of Traject is a discretized trajectory.
Yeah.
And between 2 points, so it'll have an overapproximation of the robot at 2 discrete points. And really what it'll do is just slide the geometry between those points. So it's kind of like a linear interpolation.
So would you expect that if you like turn the discretized, points not ridiculously high, even to like an unfeasible amount of discretization, that would not crash, or?
Yeah, so I would expect if you crank up the number of discrete time steps, each of these methods would become more and more safe. But they would also become more difficult to solve because they're increasing the number of constraints.
So the fundamental difference here is that because you're using the interval in arithmetic, you don't suffer from that challenge.
Exactly. Yeah.
Will be given the same initial set of waypoints. Because to my knowledge, Sparrows isn't doing that kind of path planning you mentioned as the first step.
Yeah, so at least in this example, none of these methods were given waypoints, or the best way to think about it is they were given one waypoint, and that waypoint is the goal.
Start and goal, so they
Yeah.
all had to do their own path
Yeah.
planning as well as the trajectory.
Yeah, exactly. So we also compared against Chomp. And we did initialize Chomp with a cubic spline. So this had more access than just the goal. Yeah, so here's a comparison to these baselines where we vary the number of obstacles between 10, 20, and 40. And in each of these cases, Sparrow significantly outperforms the baselines.
Why does yours crash?
Ours does not crash.
Because you get stuck in a local.
Oh, are you asking why? So these are the number of successes, and red, I'm showing the crashes. So there are some scenarios that we weren't able to solve. Yeah, and I think you were saying that Sparrows is getting stuck in a local minimum, which is definitely possible, right? Because we only give Sparrows the goal, and it's sort of a greed. If you do that, it's kind of greedy, right? So it's bound to get stuck.
So it's.
If we increase the time intervals, our reachable set should become less overapproximated. But the optimization problem will get harder. Yeah, so we would, if we had one time interval versus a million time intervals, we would never crash.
So, I mean, when I say length of the character. You reduce the number of the variables. Stop one or
That's an interesting question. We haven't tried that. I mean, the reachable set would look,
because I guess all of these methods spectrally to be as you successful, but I'm guessing the course stays successful much lower and smaller numbers.
yeah, I think, so are you talking about pure successes or just remaining collision free?
Yeah, success is like stuck. Success rate is good as you're making it small.
So I think, if we could do infinite, like essentially infinitely many collision checks, then I think these methods would perform a lot better. Especially a method like Chomp, which is really doing, I would say more global planning than what we're doing, which is really local trajectory planning. Okay, so as I mentioned before, we compared Sparrows to one of my previous methods called Armor. So both of these methods are building reachable sets of the robot. So one question is, why is Sparrows outperforming Armor so significantly? And the reason is because Sparrows is generating reachable set that's much tighter than the reachable set constructed by them. So both of these robots are following, they're both following the same. They're both following the same path, right? Both executing the same motion, but Armor's reachable set is far larger. So this is what it would look like if you visualize the Armor and Sparrows in a planning scenario. And so again, Armor and Sparrows, they're executing the same motion. And you can see that Sparrow's reachable set allows the robot to pass through this thin border of obstacles. And Armor's reachable set is in collision. So if we were actually doing planning, Armor would either not be able to solve this problem, or would have to slow down to make obstacles. And so what this is really showing is that Sparrow's reachable set allows Sparrows to generate, to not only pass through narrow corridors, but to move faster because its reachable set is less conservative.
I'm just like confused by the term reachable set because like in my mind it's like all possibilities of places you can go, but then you're restricting you're saying that you have a tighter reachable set so that your set of possibilities is smaller.
So I wouldn't quite say it like that. I would say that Armor and Sparrows are constructing the reachable set differently. And as a result, Armor is more overapproximate.
But so like the reachable set of Armor, your arm could actually go to all those locations, right?
So the trajectory that the robot would follow wouldn't actually visit those states. So right, I could build a reachable set for, imagine me being a robot and I can take one step. but I could just build an arbitrarily large reachable set for this trajectory that I'm specifying,
Okay,
even though I'm never gonna visit those states.
Mhm.
So that's essentially what Armor is doing. So there's some computations under the hood that's causing it to be more over approximated.
again, yeah, I guess I just didn't understand it. Like, so under the assumption of a trajectory that you're already gonna take.
Yeah.
like,
Or a possible family of trajectories that the robot could follow.
Can you say more about like what that family looks like in one of these like cube planning examples, like what? Yeah,
Yeah, so one example would be similar to the one I provided earlier. So the joint position would be it would be specified by an initial position, an initial velocity, and a constant acceleration. Right, so Q0 plus Q0 dot times time plus 1/2 k t squared. So it's parameterized by a constant acceleration.
and so that would be for like each of those intervals in your trajectory, you pick a different one, or?
So it would be, let's go back. So this would be one trajectory. And then we chop this trajectory up into a bunch of little pieces.
And each of those pieces, there's a different K or no?
It's the same K.
So like in the really cluttered environment or whatever, like, is the trajectory you're actually finding in the success cases a constant acceleration trajectory like that?
So, in these experiments, we're not using those trajectories. We have used them in the past. Here we're using more complicated, Bernstein polynomials.
Gotcha.
And so there, the trajectory parameter corresponds to more of a delta change in position for each joint.
I guess what I'm confused about is like, if you're computing a reachable set approximation for like all possible choices of K, if I understand correctly, like that set says for no matter which of those Ks you picked, like you'll be in the set. Like, that seems like it would be a hugely over approximative thing, or is it that like you get a different approximation for each value of K?
So one thing I probably didn't really say very clearly is, so if you imagine building a reachable set for all possible values of K,
Mhm.
when you choose a K, you essentially slice the reachable set and you make it smaller.
So there's an easy way to do that slicing that you're applying. The
Yeah,
thing. Got
so
Okay, that's
it
what
just, yeah, it just means that we just plug in numbers
got it.
and we reduce the size of our reachable set.
Understood. Thank you.
For the same constraints are the same. The calculation is the calculation make a difference.
Exactly. And so all of this, for us, all of this happens within a numerical optimizer.
All of the.
So we aren't doing that, but in the learning context, we have been kicking around this idea of, building these reachable sets, which I think we can do somewhat quickly, and then just sampling, right? And then trying to identify which trajectories are safe. All right, so I'll go through this slide pretty quickly. But essentially, we evaluated the performance of spheros on a bunch of scenes with geometry looks a little bit more realistic to what you might find in a real environment. So things that look kind of like shelves and kind of like walls and kind of like bends. So in each of these cases, I guess it won't be a surprise, spheros is able to reach the goal. We also looked at multi-arm planning with spheros. So on the left, there's an example of two-arm planning. On the right, there's an example of three-arm planning. In each of these cases, we're solving one giant optimization problem instead of 2 or 3 separate optimization problems.
Do you have examples where they're closer together? Because I feel like this is just like individual.
Yeah. So the main thing with this experiment is to demonstrate that we can actually plan with more degrees of freedom.
Yeah,
Yeah, so this would be 14 degrees of freedom, this would be 21 degrees of freedom. Maybe in this example on the right, they might be closer together.
Does the SDF account for the other, in addition to the obstacles?
No. So we've erected a small barrier, an invisible barrier between the robots. I probably won't talk about it today, but I'm actually currently working on sort of a novel self-intersection constraint that'll actually allow us to do sort of general bimanual motion planning. Are there any questions about this? Okay, so everything I showed you was in Sim for sparrows, but currently working with a really talented master student named Jan, and one of the things he decided to do was instead of building these reachable sets directly from polynomials up to arithmetic, he decided to learn those reachable sets and then apply conformal prediction from uncertainty. So what he did was he built a data set that's characterized by the initial position, the initial velocity, and the trajectory parameter. So these were the trajectories I was describing earlier. And the targets in this data set are the centers and radii for an individual trajectory, and then the corresponding reachable set. He then trained a center network and a radius network. And then this is what the output looks like. So I'm showing ground truth here on the left, and then on the right is the prediction buffered by a measure of uncertainty quantification. And so Jan was able to prove this really nice theorem that says if the sign distance between learned reachable sets at time step I between obstacles is greater than 0, then this means that the probability that the true reachable set of the robot is collision free, and it's lower bounded by this term, with this user specified. So essentially we have this empirical notion of uncertainty, and what he saw is that if he satisfies that, then the performance of pros, which is his method, closely matches that of sparrows. So for 10 obstacles, they're identical, and then for 20 to 40, pros get slightly fewer successes. Lastly, Jan was able to put this directly on hardware. So here are 3 examples. The arm is reaching between a wall shelf and a cabinet, from below the cabinet to one of the bins, and then from a bin back to the shelf. And so this is planning in real time using the learned safety representation.
I think I understand the difference between.
So the difference between pros and sparrows is that we're using a learned reachable set rather than constructing it.
Is this faster?
Yeah, so it is faster.
So can you clarify again, just like how are you learning the reachable set?
We're just using supervised learning. So we store all the centers in the radii, and then we have separate networks that predict them.
It's faster by your network.
Yeah, so we just have some loss function background, et cetera.
Speak of it.
How long does it take to produce a plan? So we still keep the same planning time limit, which is half a second. But in general, we see, I don't remember the exact numbers off the top of my head. But we do see an improvement in the planning time. I will say that the bottleneck seems to be the exact sign distance function that we're using, which is really, really heavy computation. But evaluating the collision avoidance constraints is really fast because it's just inference through a neural network.
Same.
Could you repeat the first part of your question?
Under a given budget with growth then.
That's a good question. So we didn't perform that experiment, but I think that's something it's something we should do.
Because here you're assuming they both.
I'm assuming that each of them have half a second to generate a plane.
Oh, I see, but still pros is slightly under.
Yeah, I mean, it's not exact. It is a learned model.
You would expect that if you make it slightly second.
So I'm not going to talk about it today, but I do have a paper in 2023 where we did something a little bit similar. And what we saw is that under this sort of nominal condition of giving, you know, the computed reachable set and the learned reachable set the same amount of like half a second, the learned reachable set performed worse. But once you started to decrease the planning time, the learned reachable set performed a lot better. So at least in that other paper, we were able to generate plans up to 20 times a second. So it was much, much faster. I would expect that this method is slower because in this other paper, we were learning an articulated sign distance field of the robot. Here we're outputting thousands of spheres. So I would expect this to be a little bit slower. Yeah, so here we're assuming, at least in everything that I've told you so far, all of the obstacles are axis aligned cubes. And what we're doing is we're taking the center of every sphere, and we're projecting it onto every face of every obstacle and every edge of every obstacle, and creating the distance to all the corners of every obstacle. So we're doing a bunch of computation that is maybe overkill, but that's how we're finding the minimum sign distance.
I'm gonna ask you all to hold your questions because we're at 4 p.m. now. You can have like 5 minutes maybe to
Okay.
finish your talk.
All right, so this will be very fast. Gaussian splatting is really interesting. And the goal in this part of the talk is to use Gaussian splats to do trajectory planning. Okay. And so what I'm gonna try to tell you is how to enforce safety. The problem is the same. We still want to move the arm from some initial configuration to a desired configuration, but we're going to relax our strict collision avoidance constraint, some notion of risk-aware collision avoidance. Okay. The assumptions are mostly the same, but instead of modeling the obstacles as boxes, we're going to model the scene as a Gaussian splat. And the key idea is that I will derive a bound on the probability of collision between a sphere and a normalized Gaussian splatting model. And the derivation of this bound comes directly from the volume rendering equations. Okay. You can render volumes by shooting a bunch of rays through a scene and then estimating rendering density and the color at each point, right? And then once you have the rendering density, you can compute this term called the transmittance, which is essentially the probability that a ray traveling through the scene along some interval can travel along the interval without collision. Okay. And then I'm not going to talk about color, but here's how you compute color. So you can take the rendering density, transmittance, the color at a point, and you can get an expected color along the ray. Okay, I have to move quickly. So here's a really, really quick overview of how volume rendering works. Splats. We estimate our rendering density using a collection of Gaussian basis functions. We can then transform those Gaussians into camera coordinates, and then we can transform them to camera rate coordinates. And then we integrate out, if we integrate the Gaussians along the depth, we can splat them on image plane. So the splatting and then recombining is what gives you images. And then on this side, there are a bunch of law terms that you can use to backpropagate the error and then propagate the Gaussians in the road space. Okay, So here we only care about Gaussians in world coordinates. Okay, so here's how the probability of collision, here's what the probability of collision looks like. I'll just start with a single sphere, the scene represented by a single Gaussian. I'll define a random variable, representing the direction of a ray that is randomly cast from the center of the sphere. So yeah, a direction, random variable describing the direction, and then a random variable describing a random ray. And then we can use the transmittance to calculate the probability that a random ray going from the center, goes from the center to the surface, experiences a collision while going from the center to the surface, okay? And then finally, we define the probability that a sphere is in collision, as a probability that any ray experiences a collision with some risk threshold greater than alpha. So basically, we're shooting rays from the center of each sphere. And if those rays collide with probability greater than alpha, we'll consider that to be a collision. Okay, so now that we have our expression for collision, we want to bound this by another risk threshold beta. And I won't derive this, but we essentially have a theorem that that specifies a bound. And then the most important thing to take away from this is that it contains a volume integral of the rendering density over the sphere. And so this is a term that we can actually evaluate. Here's what that looks like. So again, we have our sphere, we have our scene represented by a Gaussian. We can rotate the Gaussian so that the Gaussian becomes isotropic. This doesn't change the domain of integration, which is the sphere. We can then overapproximate the sphere using a cube, right? So we've gone from integrating over an L2 ball to an L infinity ball. And then because the Gaussian is now isotropic, we can separate the integrals. We're here, eta prime sub n is just the normalization constant of the Gaussian. And then we can evaluate this analytically using the error function. So the nice thing is that this is analytical, and it's differentiable. So we can plug it into our optimization problem. Okay, so this is what the bound of this volume integral would look like if we integrated over multiple Gaussians. So the form is basically the same. So just turn into a sum. Okay, we can rearrange the terms a little bit and then plug this in as a constraint in our optimization problem. Here's what this looks like in simulation.
You can take a few more minutes, but
Okay.
I won't let it go beyond 4:10.
Okay, so this is the last slide. So here's an example of this method working in this living room scenario that I've been showing. Probably be a good time for questions.
Why do you want to plan in Gaussian splats?
Why do we want to
Like, what are the
plan?
advantages of that representation?
So up until now, everything I showed you assumed that all the obstacles were cubes, right? And I assumed that I knew the size, the location, the shape, etc. I think in practice, that's pretty restrictive. And I think many other times we want to build a scene representation that doesn't necessarily account for every little obstacle that's in the environment. That's one. It's really nice having an explicit visual representation like a Gaussian splat compared to something like a NERP. Because if you were to change the scene, I think it's a little bit easier to think about how you might update the Gaussians if you sort of move things around. What was the third thing I was going to say? I can't remember.
That could be.
Okay, all right, so that's it. I will leave you with two questions. The first question is, are spheres all you need? And the answer is probably no. But I do think that it's a useful representation because spheres work well with different kinds of visual scene representations like point clouds or sine distance fields. So I didn't talk about either of these, but I did show that we can do planning in Radiance fields represented by Gaussian splats. As I mentioned earlier, I'm actually extending my work on sparrows to include contact constraints and self-intersection constraints for bimanual manipulation. And then lastly, some work from others in the lab has shown that you can use these kinds of reachability-based trajectory optimization problems as safety layers for robot learning. And then I'll leave you with one more question, which is probably somewhat provocative, but hopefully it's a call to action for you guys to join me on the biology side. And that question is, when will robots win the Nobel Prize? Thanks.
We have one more question about biology, but you're saying, yeah,
Let me end the session. Maybe you can take it offline. All right. Thank you, John, for your wonderful talk. We have many questions. Actually, there are some in the Zoom session as well, if you want to take them later. But yeah, thank you.